Today, we are diving into something that honestly sounds like it was pulled straight from a sci-fi movie. We're talking about a new sensor technology that's so small and so powerful, it's set to completely change how we and our machines see the world. Let's get right into it.
Seriously, just stop and think about that for a second. What if the camera sensor in your phone was 1,000 times smaller, but at the same time, it could see everything? I mean, the entire spectrum of light, from heat signatures in deep infrared all the way to the invisible world of ultraviolet. This isn't just some cool idea for the future, it's the very real promise of the tech we're going to break down today.
But to really get how massive this breakthrough is, we first have to understand the problems it's solving. So let's take a quick look at how the camera sensors in pretty much every device you own actually work right now.
Okay, so at the heart of almost every digital camera is something called the photovoltaic effect. It's pretty straightforward. A particle of light, a photon, hits a silicon sensor, and if it has enough energy, it knocks an electron loose. That creates a tiny little electric current, and that current becomes a single pixel in your photo. But here's the catch, and it's a big one. The photon has to have enough energy. And that one little requirement? Well, that's where all the limitations begin.
Right, so that enough energy rule is the real bottleneck. See, conventional sensors have what's called a band gap. You can think of it like a minimum height requirement for a photon to get detected. This is what limits them to only seeing specific slices of the light spectrum. Plus, as we try to make these sensors smaller and smaller, they start to get really inefficient, all because they rely on these relatively clunky structures called PN junctions.
So the mission was pretty clear. How do you build a sensor that doesn't have a band gap and can be made impossibly, ridiculously small? Well, a team of researchers, led by Dr. Mohammad Razak, figured it out by basically throwing the old rulebook out the window.
And this is it. This is the hero of our story, the nano-Schottky junction. And let me be clear, this isn't just a small improvement, it's a completely different way of seeing light. It works on a principle that's fundamentally different than any camera that's ever been built, and it all starts with a design that is just beautiful in its simplicity.
So what is this thing? You're going to love this. You take a single, tiny metal nanoparticle, we're talking 5 to 20 nanometers wide, which is smaller than a virus, and you just place it right on a silicon base. That's it. That is the entire sensor. No complicated layers, no doped silicon, just a tiny speck of metal on a semiconductor. This is just a totally different way of thinking. The old, complex PN junction? Gone. Replaced by a simple metal to semiconductor surface. The old photovoltaic effect? Out. In its place, we have something way more exotic, quantum tunneling. And the star of the show isn't layers of specially treated silicone anymore. It's just one single, tiny metal nanoparticle. So here's the key. This incredibly simple new structure unlocks a truly bizarre and incredibly powerful phenomenon from the world of quantum physics. This is the secret sauce. This is how this tiny sensor can see literally everything.
Probably the best way to get your head around quantum tunneling is to use this analogy. So in our normal everyday world, if you don't have enough energy to climb over a wall, you're just stuck, right? But in the weird world of quantum mechanics, particles like electrons can do something that should be impossible. They can just appear on the other side. They tunnel straight through the barrier. Okay, so here's how it all plays out with this new sensor. First, a photon of light hits that metal nanoparticle, and this is the most important part. It can be of any energy level. An electron inside that particle absorbs the energy. But instead of needing to get enough power to jump over a big energy barrier, that electron just takes a quantum shortcut. It tunnels right through the gap into the silicon. And that movement creates a detectable electric current. It's a signal made from almost nothing.
And don't just take my word for it. The lead researcher, Dr. Mohammad Razak, explained it perfectly. He said that because these nanoparticles don't have that restrictive energy band gap, they become super sensitive to any wavelength of light. It's like this sensor becomes a universal key that can unlock a signal from any photon that comes along.
All right, so we've got a tiny sensor that runs on quantum physics and can see all kinds of light. That's cool. But what does that actually mean for performance? What are its real-world superpowers?
First off, let's talk about resolution. The active part of these sensors is less than 10 nanometers. To give you some scale, a single strand of your DNA is about 2.5 nanometers wide. We are literally talking about a pixel the size of a molecule. This allows for a density and a level of detail that, until now, was pure science fiction. I mean, look at this comparison. The leap in what this thing can do is just incredible. The spectrum it can see goes from a tiny little window to basically everything.
The sensitivity is so high it can detect a single, low-energy photon. And the size difference, it's mind-boggling. We're moving from the world of the microscopic to the truly nanoscopic.
And what's even more amazing is that this discovery isn't just about using gold nanoparticles. This technique opens up a whole new toolbox. We can start using other advanced materials, things like nanowires or tiny crystals called quantum dots, even single-atom-thick nanosheets, to build the next generation of sensors. We are at the very start of a new materials revolution.
So let's zoom out. Where is all this headed? When you create a technology that is this small, this sensitive, and this versatile, you don't just improve old gadgets. You start to create possibilities that never even existed before.
Think about it. Cameras so tiny they could travel through your bloodstream to find disease. Environmental sensors so sensitive they could detect a single molecule of a pollutant in the air. Fiber optic communications that get a massive speed boost. Brand new tools for science that could let us watch chemical reactions happen in real time. This isn't just an upgrade, it's a whole new way of doing things.
Ultimately, what this technology really does is give us a new set of eyes. And that leaves us with one final and really exciting question. Now that we have the ability to see what has always been invisible, what new worlds are we about to discover? Both out there in the universe and deep within the fabric of matter itself.